Hello friends, this is your Professor Samir Sheikh. I am working as an assistant professor in NB Naval Singh College of Engineering, having more than 15 years of experience in teaching. This is my current profile. I have done MTech in CAD, CAM and automation, and I am also CAD qualified. So, in the previous lecture, what we have seen is the features and advantage of CNC. In today's lecture, we will try to cover what is adaptive control and what are different machining parameters that will affect the adaptive control. Before we actually want to know what is adaptive control, let us try to understand what is the need of adaptive control. See, NC and CNC, basically these machines, which are very high profile automated machines, are basically used to reduce the non-productive time in manufacturing. In conventional machine, the challenge is to reduce the non-productive time as well as to reduce the machining time. So there are two factors. One is non-productive time and second one is the machining time. In non-productive time, if we talk about the factors which can affect it are work handling. That means transferring the part from one station to another station. It consumes time, so it is a non-productive time. Job or machine setup is also going to consume your time. Lead times between order and actual production. That means the time where you get the order and you plan the order and you try to execute actual production is also going to affect your timing. This time should be obviously very short. You should plan very fast and put that order under production as soon as possible to reduce your lead times. Also, tool changes are going to affect the non-productive time, and of course the human factor will also play a very big time consuming factor. So operator delays in one most factor. Most of the things are now in place wherein you can actually put this thing under constrained conditions, so you can reduce the non-productive time as and when you want to. So looking at the broad picture, we can say that total production time is nothing but non-productive time plus machining time. So that will give you a complete production time for a particular object. Okay. So reduction in non-productive time means more time is spent by the machine in actual machining. So if I control this factor over here, if I want to reduce it as much as possible, my time is now been consumed in machining. If I control this factor also, and if I am able to control these two factors in all very effectively, I am completely reducing my production time. So basically, as you know that NC CNC machines, which are basically used for machining fast as compared to conventional machines, are having very high hour rate. That means if I use these machines for my manufacturing, I am making sure that the production rates are very good. That means non-productive time as well as machining time are under control. It should be ideal, it should not be ideal for longer times, and it should do the machining at optimum speed. That means when I am using NC or CNC machine, the machining time should be controlled. Non-productive time are of course factor which plays in total production time, but when I talk about adaptive control, I am mostly focusing on machining time. How can I control the machining time, or how can I optimize the machining time? Okay. So in conventional machine, basically we can't do much about reducing the in-process machining time. Lathe machine or turning machine, basically conventional machining, the in-process machining time where the operator, a person, a human works and reduces the material, removes the material, we cannot do much about it because it varies from person to person, it varies from operator to operator. So there is not much scope to work with in-process machining time in conventional machines. But when we talk about NC and CNC machines, where the operator is not doing machining, the machine is doing the machining. So what basically we do is, the part programmer takes care of the cutting speeds, feed rates, depth of cut, etc. in the part program. So whatever things we need for machining that particular component, the part programmer takes care before writing the part program or while he writes the part program. So these things will come based on his knowledge and his experience to achieve the desired outputs such as accuracy, surface finish, etc. and etc. So basically, part program is the person who specifies the cutting speeds, depth of cut or various machining parameters so as to get the desired output. So we can say that the operator may not, the programmer may not be having enough utilization of the CNC machine. So the person is not using his experience, his knowledge to make sure that the CNC machine with which he is going to work is working under optimal conditions. It may be underutilized, the machine may be underutilized, or it may be overburdened with these cutting parameters. So we are not sure that whatever cutting speeds, feed, depth of cut we are using for a particular part are enough for the CNC machine. So we have to make sure that these things work in coordination with the CNC machine. So as you can say that there are two factors, productive time and non-productive time and machining time. So the concept of adaptive control comes in a place which says that adaptive control aims at reducing the in-process or machining time in a manner so that optimal machining capabilities are taken into consideration. Okay, so we are going to focus on in-process or machining time. During machining, whatever parameters are there, we are going to control them so as to utilize the optimal machining capabilities. Right? This we are going to do in real time. While we do the machining, we are going to make sure that these parameters are controlled. Okay, so what are the parameters? The parameters are feed rate, cutting speed, depth of cut, etc. So once again, let me repeat. The concept of adaptive control aims at reducing the in-process or machining time in a manner so that optimal machining capabilities are taken into consideration. Right? Now adaptive control, when we apply, is basically the parameters go on adjusting automatically. When we apply adaptive control, cutting parameters go on adjusting automatically. By implementing adaptive control concept during machining so that we can maximize the available spindle power, limit deflection of cutter to its permissible value, limit the cutting tool temperature to its permissible value, and of course we can also limit the vibrations of the cutter to its permissible value. Now these parameters, if we control while doing the machining, we are making sure that the machine is used to its optimal capabilities. Now what are the things, what are the areas, applications where we can use adaptive control? There are basically 5 variable machining conditions where we can use adaptive control. Let us look at them one by one. First is variable geometry of cut. Variable geometry of cut due to changing depth of cut or width of cut. As you can see in this figure, there is a cutting tool which is going to cut the material along this particular slot. As and when we work with conventional machines, or if we use a part program which does not have adaptive control, the feed rate is same at this corner as well as at the end of this slot. So as the tool moves towards the left side, the feed rate does not decreases in such situations. Now because of this, there might be large amount of forces acting on the cutting tool as the material removal rate is increasing. So it might affect the machining parameter and the tool might get broke. So in such cases, if we control the speed, if we can control the feed rate, and if we able to reduce the feed rate, we are making sure that the machine is not overloaded. So feed rates can be reduced if depth of cut or width of cut increases. Such situations comes generally in machining, profile milling, or contouring operations. The second point that we are going to discuss is variable workpiece hardness due to presence of hard spots and non-homogeneity of materials. In this figure you can see that while doing the machining, as the cutting tool is moving towards the right side with certain feed rate, a hard spot has come into picture. Now of course you know that hard spots and will come because of the material homogeneity and non-homogeneity. So during the manufacturing of the raw material, these things can come into picture. But while machining, if such things come into picture, we need to make sure that the feed rates are reduced to prevent the excessive tool wear and hence prevent the tool failure. So such things, if are not applicable in if we are not able to identify such things in conventional machining, or while a part programmer writes a program without considering such situations, it might give more tool wear and it might happen that the tool will fail. Okay, so while we adapt to control concept, such things can be controlled dynamically in real time. So the cutting tool will understand the amount of force it is taking to reduce the hard spot, and accordingly it will reduce the feed rate. Okay, so it's a real time work. The next point is variable workpiece rigidity. As you can see in this figure, this particular cross section is having thin sections. The material here is very less, and of course the way it is been mounted is also not very good. But we have to do the machining over here. That means if I do a machining operation over here with certain amount of forces, it might bend the workpiece, right? So deflection of the workpiece will result into rejection of the part. So deformation can take place. So we of course want to avoid such situations. So to maintain accuracy of workpiece, feed rates must be reduced over here. So it depends on the workpiece, and if we come across thin section workpieces, the system should understand it will bend the object or it is going beyond certain limit, and accordingly it should reduce the feed rates. Next point is air gaps during cutting. As you can see in this figure, there is a workpiece, there is a C channel over here. From this part to this part, of course we are going to get more forces coming over the spindle and the cutting tool. So the feed rates are in a controlled condition. As and when it comes to this point, there is an air gap here. So the machine should understand that here no material is present. So the cutting should take place at higher rates so as to reduce the machining time. The machining time generally increases 2 to 3 times the normal feed rate. So such thing is also applicable while adaptive control is under consideration. Last point is tool wear. As you know that when we are using very sharp or very new tools, the cutting forces are very less. That means these new cutting tools will remove the material at a very good speed or good condition. But as and when the tool starts to wear, more and more cutting forces will act on the cutting tool. In such cases, feed rate should be reduced. So that way also we can use adaptive control to work real-time situation in machining conditions. So these were the 5 situations where we can use adaptive control to the optimum utilization of the machine tool. This is all about this session. In the next session, we will work with types of adaptive control and advantages of adaptive control. Thank you.